So there'll be a few things you may not be quite familiar with on this one as well, but I was going to go over it because basically what all these questions are about reactions. They're about balancing reactions, which is something we definitely need some practice doing. It's about calculating the yield of reactions, which really isn't something we've done a lot of so far, and a lot of stoichiometry, which is just basically looking at the balance of reactants and products and making sure we can calculate the amount of product based on the amount of reactants, or if we measure the amount of products, just like you did in your lab yesterday. Basically, you did a reaction where you measured the amount of a product, and then using a balanced reaction, went backwards and figured out exactly how much reactant was present. And that's what stoichiometry basically is seeing what the ratio of reactants and products are from a balanced reaction, and that is key. That's something we're going to do today. And being able to figure out, if I have so much product, I'll have this much reactant. And we're also going to be dealing with the concept of limiting reactants. If you're doing a reaction and you have a certain amount of reactant A and a certain amount of reactant B, you can't always assume that all of it is going to be consumed and you're going to turn it all into products. That we know that doesn't happen because we may run out of one of the reactants before we run out of the other. And so we're going to go over how to figure that out. How do you figure out if you're going to run out of reactant A or reactant B first? And if we do run out of one of them, what does that mean for the amount of product that we're going to form? Those are basically called limiting reactant problems, and we're going to do a number of them today. So, who has some questions before we get started, and then we'll dive in.
Some questions regarding this, or
anything at all.
Just to start with the first one.
Sure, yeah, we definitely could start with the first one, because there's probably, I bet you don't know what the brackets mean, do you? Is that what probably your first question? Okay, yeah, we can start with number one. Is there any other questions before we just jump in and start working on these? Because if not, we're going to jump in and start working on these.
Yeah.
Okay, cool. All right. So yeah, basically start with something you've got right in your kitchen right now, I'm sure. So you got a solution of vinegar. And so we know that vinegar is acetic acid. It's just basically dilute acetic acid in an aqueous solution. So the rest of it is water. And so let's look at the information we have. So we know it's 4% by mass. So let's write that down. Let's figure out what that means as well. So 4% by mass. Anyone tell me what that means? So if a solution is 4% by mass, what does that actually mean? Because you guys had to do this calculation on your lab yesterday. Hopefully you know what it means.
No.
Nope. Uh-oh.
Can.
Well, someone take a stab at it. That's what these recitations are all about. I don't want you to have all the answers. If you had all the answers, we wouldn't be doing these. I want to find out what it is you know now, and if it's not exactly what we're looking for, hopefully we'll sort of guide you to find the right answers. So somebody was getting ready to give a guess here. What do you think percent by mass means?
Like out of all the mass in the solution, 4% of that value is the amount of mass the acetic acid is.
Exactly. Man, see? Exactly right. So what it means is when you say percent mass, there's two parts of a solution. One is the solvent. Okay, so the solvent is the thing there in the highest amount. So generally in an aqueous solution, the vast majority of that solution is water, right? We don't think of air as being a solution, but actually it is. It's a solution of gases. And because nitrogen is the most abundant gas in the atmosphere, it's about 78% or so, we say that the air you breathe is a nitrogen solution with all the other gases dissolved in the nitrogen. So 4% by mass means if there's two parts of a solution, one is the solvent. What do we call the other one? Anyone know what we call the other one? The thing that's actually dissolved in the solvent. What do we call that?
Solute.
Solute, exactly. Very good. So what 4% means, what's the percentage of the mass of the solute over the mass of the solution? And notice this isn't the mass of the solvent in the denominator, it's the mass of the whole thing. So as the other speaker pointed out, yeah, it's the percent of one thing versus the amount of everything. And that's why we need the density, because we're not going to be able to figure out what the mass of a liquid is unless we have the densities. We generally measure liquids in volume, right? We measure liquids in milliliters or liters or something, or gallons or whatever. We generally don't measure liquids in grams. And so what we're going to do is just assume we have 100 mils, because that'll make our math easy. So if we have 100 mils of vinegar, what's the mass of the vinegar? So I have 100 mils times something will give me the mass in grams.
Density.
Right, we'll multiply by the density. So where do we put our grams and where do we put our mils?
It would just be 100 times 1.04 over 1.
Yeah. Units, remember, always put units in there. So 104 grams over
1 milliliter.
1 milliliter, exactly. Always have the units. I'm going to keep harping on this until, well, you're probably already tired of me harping on it, but I'm going to keep doing it. Because when we multiply, we get rid of the mils because we have mils on top. We have mils as a numerator, mils as a denominator. They cancel out. We're left with grams. And so 100 milliliters of vinegar would have a mass of 104 grams. So what's the mass of our acetic acid? Oops. What's the mass of our acetic acid in there? So I've got 100 mils of solution. The total mass is 104 grams. What's the mass of the acetic acid in this 104 grams? Well, what do we, from the question, what do we know about the relative abundance of the acetic acid in the solution? So if the total mass is 104, what's the relative mass of the acetic acid by itself?
Like it's gonna be 96%.
What's 96%?
I just say 100 minus 4. I'm not sure.
Why are you subtracting 4? What does percent mean? I mean, yes, you're right to refer to this, But what does percent actually mean?
4/100.
Wait.
So yes, 4/100. What do we do with that 4/100?
Add it to the mass.
Add it to the mass?
No,
Multiply it.
multiply it to the mass.
Multiply it by the mass, right. So if the total is 104, the mass of the acetic acid is 4/100 of that. So what's our total mass of acetic acid?
I have a question. How did you get 100 mils in the beginning to start off?
I just made it up.
Oh,
We could use whatever volume we want. We'll get the same answer. I could have used 200 mils. I could have used a liter. I could have used 1,000 liters. It doesn't matter. I just used 100 mils because it makes our math easier. That's all.
oh, okay.
Yeah, that's it. You're free to use whatever volume you want. Because you see that the question doesn't have a volume. So basically you have to make up a volume and go from there. And the point is, no matter what volume you chose, you're going to get the same answer.
So it's going to be 4.16
So 4.16 what?
grams.
Grams. So the amount of acetic acid we have is 4.16 grams. Now, this expression right here in the square brackets means molar concentration. So square brackets, chemical, whatever it is, in this case, acetic acid. Acetic acid is HC2H3O2, square brackets, means what is the molar concentration in moles per liter of acetic acid. So right now, let's look at the information we have. We have two pieces of information. We have the mass of the acetic acid in solution, and we have the volume. And that's really all we need. We need moles divided by liters. And so we have amount, our amount is 4.16, and we have our volume, that's 100 mils. So what's our next step? What do we need to do?
Convert the volume to liters.
Okay, let's do that first. So 100 mils in liters is what? So 100 mils times something gives us liters. So we want liters on top, and we want mils on the bottom. So how many milliliters in a liter?
1,000 milliliters.
1,000, that's right. So how many liters does that give us?
1.
Nope. It's 100
0.1.
times this. 0.1, yes, that's right. So 0.1 liters. And since we didn't give significant digits to our volume, we're just going to assume, we can assume however many significant digits we want. We could assume that it was 100 mils. We could assume it was 100.000 mils. We can make it whatever we want. Basically, what we'll be stuck with is the significant digits of our density over here and our percentage over here. So how many significant digits are we going to have in our final answer?
3.
3, that's right. So we're going to have 3 significant digits in our final answer. So far we have, so for our molar concentration, we have our liters. That we have, but we need this. How are we going to figure out moles? Because that's really what we're interested in. How many moles in that volume?
Would you find the molar mass of the acetic acid?
Yep. Yeah, so two ways. You can either just look it up, which is fine, or take the mass of 1 hydrogen, 4 hydrogens actually, 1 here, 3 there. So 4 hydrogens, 2 carbons, and 2 oxygens. Or just look it up. Either one.
So in a test, we'll most likely just solve it ourselves. It wouldn't be that big, or would it be?
Well, on a test, you're going to be doing it at home, right?
Oh, okay. So we could just,
So you can just look it up. Yeah, you can.
Okay.
Duh. That's what a chemist would do. That's what I would do. I'm not going to sit here and calculate and let Google tell me what it is. I'm not a dummy.
Professor, just a quick question. 416 is the mass of the solution.
That's the mass of our acetic acid. If you remember, the mass of the whole solution was 104 grams because of the density was this, and I decided to use 100 mils.
So
the
the whole
total-
solution is 104.
Yes.
But how acetic acid is bigger than
No,
100?
4.16. 4.16.
Okay.
Yeah. 4.16. So some genius looked up the molar mass of acetic acid.
60.00 grams over mole.
Really, 60 right on the nose, huh? 60.00 grams per mole. Okay. Now, I need to use this to calculate how many moles are in 4.16 grams. So what am I going to multiply my 4.16 grams by to get moles of acetic acid? Now remember, at the end, I want moles at the end, and I want my grams to cancel. So I need to multiply my 4.16 grams by something.
Is it 1 mole over 60 grams? 60
It really is, because that's why I always want to do multiplication, and I always want to leave my units in there, because this way I will remember that grams cancel. There's my 4.16 grams canceling, 60 grams and 1 mole canceling, and I am left with moles, and that is the unit I want. That ensures that I'm going to do my math correctly. And if you show this on a test or anything else and make a stupid mistake, I will realize you just made a stupid mistake, and you will get credit for setting this up properly, even if you screw up the math. Okay, because doing it this way tells me you understand how to change one unit to another unit. If you just change it, then I don't know how you thought about doing it, whether you just looked it up or what you did. But if you show me the method you did it, then you'll get full points. Okay, so how many moles is that? 4.16 times 1 over 60.
0.0693.
0.0693 moles. Okay, we're almost done. I have the 2 pieces of information I need to solve this question. And the 2 pieces of information I need are the number of moles and the number of liters. And I got that information finally.
So you just divide that number by the liter. The moles, 0.6.
Right, it's good. So molarity, which is what we're dealing with, that's what the square brackets means molarity, capital M. Moles over liters. And so the molarity of our acetic acid is 0.0693 moles divided by 0.1 liters. So what's the molarity of our acetic acid?
.6933 moles over
0.693. Where's the other 3 come from? Oh, is there another 3 here?
Yeah. Well,
Oh,
it's
okay.
like 3s.
Okay.
Yeah.
And what's the unit? Remember, we
Moles
always
over-
have to have a unit.
Mole per liter.
Yeah, 2 ways to put it. You could either answer it in moles per liter or capital M, because they mean exactly the same thing. That's what capital M means, is moles over liters. So Are we done? So we have the right unit and we have a number. Is the number correct?
No, because you need to do 3 significant digits.
Mm-hmm. Yes, only 3 significant digits. So what's our final answer?
0.6930 m.
Nope. You don't include the 0. If you include a 0,
Then it'd be 4.
this number also has 4 significant digits, because there's no reason to put a 0 after the decimal unless you've actually measured something that accurately. You know what I mean? So if it's before the decimal, it's a placeholder for to tell you how big the number is. There's a difference between 2 and 20 and 2,000. They all have 1 significant digit, but the difference is the number of zeros. So the number of zeros play a role in telling you how big the number is. After the decimal, a trailing 0 doesn't tell you anything about how big the number is. It does tell you how precisely you've measured that number. And so if we only have 3 significant digits, we can't have a 4th number here. We have to get rid of it.
It'd be 0.693.
Right.
No.
0.693 and then stop, because that number has 3 significant digits. Yeah, so it'd be 0.693. And what do we call this? Anyone remember what we call that?
Molarity?
Yeah, but actually the unit has a name. You're right. It's a symbol of molarity, and the unit is called. Anyone remember what it was called?
Molar concentration?
Just molar. Just molar, like the tooth. So we say the concentration of acetic acid in vinegar is 0.693 molar, and molar means moles per liter.
So in a test, would you want us to write the capital M or molar?
The unit is capital M. So you could say one of 3 things. You could say it's moles per liter, or capital M, or molar. All 3 of them are equivalent. So it doesn't matter. You could pick and choose. But remember, any answer you give has to have a unit in it, unless, of course, it's unitless. Like RF, if you remember, RF was unitless because it was millimeters divided by millimeters. So that's unitless. But if there's a unit, you have to have a number and a unit. So as long as you have some sort of unit, moles per liter, or capital M, or like write out molar, any one of those is correct.
So I have a question. How would we know when we're going to estimate the volume?
Well, we didn't estimate a volume.
Not estimate, I mean,
We chose one.
how can we?
Well, because we have a solution and it doesn't say how much the solution was. So you basically just start with a volume and just work from there. Because this, as I mentioned before, it doesn't matter what volume you chose, you're going to get the same answer of 0.693 molar. Because no matter how big the solution is, the concentration of acetic acid in is exactly the same. It's always going to be 4%. So I could have like 1 mil of vinegar that's got 4% acetic acid in it. I could have 1,000 gallons of acetic acid. It's got 4 of vinegar. It's got 4% acetic acid in it. It doesn't matter what volume you chose. You just have to choose something and start from there. Okay? Yeah, I realize it's a little confusing when you say, it's got a density. I don't know what the volume is. It doesn't matter what the volume is. You'll get the same answer. It's just like when we're doing, we're trying to figure out the molecular and empirical formula of a molecule, and you're told that there's a certain percentage of carbon and a certain percentage of hydrogen and a certain percentage of oxygen, and I recommend you choose like 100 grams. You don't have to choose 100 grams. You could choose 1,000 grams. You could choose 538 grams. It makes no difference how much you choose, because the percentages of each one will be exactly the same. So You know, I basically just chose 100 mils because it just makes our math easy. We can figure out the mass of it instantly. Or we could have chosen a liter. It really didn't make any difference. Okay, so next one. Who wants to pick the next one we work on?
2.
Go right to 2. Let me see. Yeah, there's something in here you wouldn't know about either. So this is a precipitation reaction, just like the precipitation reaction you did in lab yesterday. So let's write down everything, all the information we have. So we have 20.0 mils of a 0.285 molar solution of sodium carbonate. So we should probably figure out what the hell sodium carbonate is, right? So what's sodium carbonate?
NaCO3.
NaCO3.
I'm not sure, just think.
Actually, I can't even remember what the. Yeah, someone looked at it. I can't remember if carbonate is a +1 or -1 or a -2. I think it's a -1, but it's important for the
It's Na2CO3.
Yeah, it's 2. It is 2. I thought that. Yeah, okay, it is 2. Right. So we have a 0.285 molar solution of this, and we're going to be adding iron chloride. And so we don't need to worry about how much iron chloride. We're going to add as much as we need, basically. So now will probably be a good time to write out what our reaction is. So when we put sodium chloride in solution, so let's say we have chloride, sodium carbonate. I take some solid sodium carbonate. It's an ionic compound because it's got a metal and a non-metal. I drop it, I put it in water, and when it dissolves, we no longer have this. What do we have? What happens when we dissolve an ionic compound in water? I dissolve sodium chloride in water. Excuse me?
Participate?
No, it doesn't precipitate because we know it doesn't precipitate because we have a solution of it. If it precipitated, we wouldn't have a solution of it. So the fact that we have that right here tells me that does not precipitate in solution. It means it's soluble in water. And if something's soluble, if an ionic compound is soluble in water, what happens to it when it dissolves in water?
It breaks up the solid.
Breaks up the solid first, goes into solution second, and then what happens to it when it goes into solution? Does it go into solution as this? Would we write down Na2CO3 aqueous? Is that what happens to it?
Yes. No.
No. What happens to it?
It becomes a solid.
It is a solid. When I drop it in solution, it's no longer a solid. It's in solution now. Remember, I have a sodium carbonate solution. I don't have any solid anymore.
Would it become a liquid?
Nope. No, I would not put, so sodium carbonate liquid is also wrong. So that's not right. That's not right. And solid's not right because it's in solution. What happens to an ionic compound when we dissolve it in water?
Wouldn't they separate,
Yes.
not interact?
They separate, that is correct, and become what?
The ions are like attracted to.
They become ions, that's right. So what happens? So what happens to my sodium and my carbonate when I drop it in water?
They break apart and bond.
They don't bond. They're bonded as in a solid. They're bonded to each other when they're in a solid. When we dissolve them in water, they're now bonded to water as ions. So they ionize when they're in water. And so what are the products of sodium carbonate when it's dissolved in water? It's a chemical reaction. What happens to solid sodium carbonate when I dissolve it into water? Someone had it right. It forms ions. The question is what ions?
Negative?
What ions are formed?
Is it the polar charge ions?
They're charged, yep. But what are they? I have sodium metal ions, and I have carbonate ions. What are they? How do I represent that, writing them down? So I've got there's two parts of the salt, right? There's the metal part and there's the non-metal part. So what ions are formed from the metal part?
+2, +2.
So remember, there's two of them. What's always the charge on sodium? Always. Sodium is never +2, ever, ever, ever.
One.
+1. So yeah, you have sodium plus. How many moles of sodium plus for every mole of sodium carbonate?
2.
2, right. We get 2 sodium ions from every molecule of sodium carbonate. So what else do we get? So we get 2 moles of Na+, and what else do we get? What's left?
3 moles of carbonate,
Why 3?
or 1 mole of carbonate.
Ah, right, because it's a polyatomic ion. This whole thing is an ion. So we get 1 mole of CO3. And what's the charge on CO3?
Negative.
2.
-2, that's right. So for every 1 mole of sodium carbonate, we get 2 moles of sodium ions, aqueous, and we get 1 mole of carbonate ion, aqueous. Okay, now, what is the other part of our, so that is one set of ions in our solution. What's the other one?
Iron chloride.
Iron chloride. Ah, but it's not iron chloride, is it? What is it?
Iron 3 chloride.
There you go. Because, yeah, iron is a transition metal. It sometimes forms iron 2 chloride, sometimes it forms iron 3 chloride, and we need to know which one. So what's the formula for iron 3 chloride? Oh, no, Fe is, oops. Let me erase that. Oh, dear. Oh, I can undo. There you go. All right, so we know the Fe is iron and Cl is chloride. What's the formula for iron 3 chloride?
FeCl3.
That's right. Excellent. And we know iron chloride, that's a solution too. So basically we're adding a solution, we're adding 2 solutions together. One has sodium carbonate solution in it, and the other one has iron chloride solution in it. So this is also aqueous. So when that dissolves into water, what do we get? Just like the sodium carbonate.
3Fe Cl.
So you think we,
plus
so,
Cl.
so I think I get 3 moles of Fe and 1 Cl. So what's my charge on the iron? What's the charge? Well, charge of iron 3 should be fairly obvious, right? What's the charge of iron 3?
Plus 3.
Plus 3. And what's the charge on chloride?
Negative.
Always, always, always.
Negative 1. So it'll be 3.
Negative 1. Uh-oh, that doesn't really balance, does it? So I've got 1 iron here, and then it forms 3 ions. Then I've got 3 chlorines here that only forms 1. So what's our mistake there?
It'll just be Fe plus 3Cl.
There you go. With the charges, remember there's going to be charges. So when that dissolves, we're going to get Fe plus 3 plus 3 chlorides. So in this solution, we are going to have sodium ions, carbonate ions, iron ions, and chloride ions. And so we know that sodium plus carbonate does not precipitate. That doesn't precipitate because we have a solution of it. So that doesn't precipitate. We know that iron 3 plus chloride together does not precipitate because we have a solution of that. So we have 2 options left. Either sodium plus chloride forms a precipitate, or iron plus carbonate precipitates. Which one of those do you think actually precipitates?
Sodium and chloride.
Okay, so when you put salt into water, does it precipitate?
No. So then iron and
Yeah, because we know that sodium chloride is soluble. I mean, it's salt. I mean, look at the ocean. It's got a ton of salt in it. That's mostly potassium chloride, but still, same thing. Yeah, so sodium and sodium ions and chloride ions are super, super soluble. So yeah, they're not going to precipitate when you mix them together. But iron and carbonate will precipitate. And one other thing to look out for, this isn't something we've done, we haven't talked about solubility a lot. If you have 2 ions with high amounts of charge on them, like iron is plus 3 and carbonate is minus 2, that means when those 2 things come in contact with each other, that's a very high charge density. And they basically will come together, and they're more stable together than they are surrounded by water. So iron plus carbonate will form very strong ionic interactions. And the stronger the ionic interaction, the less soluble these things are. So be on the lookout for ions with high charge densities. So if you see something like aluminum and phosphate, if they come in contact in solution, those suckers are going to precipitate because that is a very strong interaction. If you see, basically, if you see single charges like sodium and chloride, they're generally not going to precipitate, or potassium and chloride, they're generally not going to precipitate, but high charge densities do. So we've answered one question. We figured out that our precipitate is going to be iron carbonate. So we figured that part out. Yay. Now we need to figure out, well, how much iron carbonate is going to form. So this is this. What's going to be the formula for iron carbonate?
Fe2 CO3 parentheses 3.
Yeah. Mm-hmm. Yeah, and you can see why that would precipitate, right? Because we've got like +6 over here, a -6 over here. That's a really strong interaction. They're going to want to be with each other rather than with water. So it's going to fall out. So what is our overall reaction? Our overall reaction is Fe plus CO3 makes Fe2 CO3 3. So is that a balanced reaction? Does that, we have the same number of atoms on as reactants that we do as products?
No.
You need to add
Gotta
2.
take care of that.
Add
Yeah, what do we need 2 of?
2 Fe reactant.
Yep, we sure do. We need 2 irons. And how many carbonates do we need?
3.
3, exactly. We need 3 of them. So, we're making headway. We figured out what our product is going to be. We figured out what the balanced equation is between reactants and products. Now, we need to figure out from the information we have in the question how much reactant we have, and then we can calculate how much product we have. So we know how much of this we have. How do we know how much of this we have? How are we going to figure out? I mean, we need to calculate it, but we know how much there is. Go ahead.
Is it 20 milliliters of that, of 0.285?
Yep. So we know we have 0.285 moles per liter, right? That's what capital M means. And we know we have a volume of 20 mils. So I need to multiply this by my concentration by something to give me moles.
But wouldn't you first have to convert the 20 milliliters to liters?
That's right. Yep. You want to go ahead and do that? How do you do that?
So 20 milliliters multiplied by 1 liter over 1,000 milliliters.
Yep. Oh man, you are an expert at this. How many liters is that?
0.02 liters.
0.02 liters. Yep. Okay, so what do I do with this information to give me moles?
So 0.02 liters over...
Over nothing. Yeah, we don't have to put it over anything because liters will then cancel out and I'm left with moles. So we'd have to put it over anything. So it's liters cancel, we get moles. So how many moles do we have?
0.0057 moles.
So 0.0057. Oh yeah, you're right. 0 moles. So now we figured out how much of this we have? Let's see. Oh, wait a minute. Yes. So our sodium carbonate is Na2CO3. So for every mole of sodium carbonate, we have 1 mole of carbonate ions. So whatever the concentration of sodium carbonate is, it's the same amount of carbonate. Okay, that's crucial because for other solutions, we may have, let's say, for instance, we had aluminum carbonate. I mean, that would precipitate. But if we had aluminum carbonate, that would be Al2CO3. So for every 1 mole of sodium, for aluminum carbonate, we'd have 3 moles of carbonate. So you always have to figure out if I have a solution, if I have an ionic solution, how much positive, what's the actual concentration of my positive ions? What's the concentration of my negative ions? So in this instance, we're interested in the negative ion. Now the concentration of sodium ions would actually be twice as much as this. It wouldn't be 0.285 molar, it'd be 0.57 molar. It'd be twice as much because there's 2 moles of sodium ion for every mole of sodium carbonate. Does that make sense? Since there's 2 of them, it's twice as concentrated.
Yes.
But the overall concentration of sodium carbonate is 0.285. So we're almost done. We only have about 8 more calculations to do. So we know, oh, go ahead.
In cases like this, since it's gonna fill up the whole page, do we just put it in a binder paper?
Sure. Yeah, you don't even have to write it down on, you could just, you don't have to write it on the recitation itself. If you can just write it on anything you want.
Okay.
If you've run out of room, if you don't write really small like I do, just write it on anything. I don't care. You need, right, so let's erase some of this stuff because again, we need a lot more room.
I can just stop 0057. No need for the 0 last one. The answer here.
Your final answer needs to have the right number of significant digits in it. But for right now, yeah, you could leave this out if you wanted. But so we have 2 calculations left to do. First, we need to figure out how many moles of iron 3 carbonate we're going to make, and then we have to convert that to grams. So the question is, how many moles, based on this balanced equation, we have a balanced equation here, how many moles of iron carbonate are we actually going to form with 0.0057 moles of carbonate? Now remember, we don't have to worry about the iron because it's in excess. So we're not going to be limited by the amount of iron. We have as much iron as we need, so we can ignore that. Our carbonate is the limiting reactant. So how much iron 3 carbonate are we going to make?
3 times.
Well, we need to figure out what's the ratio. Always multiply by something. So here's what we're going to do. We're going to have 0.0057 moles of carbonate multiplied by something that gives us moles of iron carbonate. So I need to multiply this by something that gives me this. What am I going to multiply it by? I need to cancel moles of carbonate and be left with moles of iron carbonate. And then good. So I need something that tells me the ratio of moles of carbonate to moles of iron carbonate. What is that ratio?
3 to 1.
What's 3 to 1?
It's 1 mole of iron
Mm-hmm.
over 3 moles of carbonate.
Yep. So that cancels out moles of carbonate. And so do we have 3 times as much or 1/3 as much?
1/3 as much.
1/3, that's right. So that is why I always, and I'm going to harp on it again and again, and you get tired of it, but always multiply, always, and have the units there. That will keep you from making mistakes like that. Because, yeah, we look at the balanced equation and we say, okay, yeah, 3 to 1. Yeah, the ratio is 3 to 1. The ratio is 1 to 3. And so if you write it out like this, with my moles of carbonate, and then I have to have moles of carbonate in the denominator and moles of iron in the numerator. Oh, it's 1 to 3. Duh. Okay, got it. And so that will tell you what you need to, what's the change you need to make. Divide by 3 or multiply by 3.
This is 3 mole of CO3?
Yeah, it takes 3 moles of CO3 to make 1 mole of product. And so I'm going to get 1/3 as much product as I have of reactant because it takes 3 moles of reactant to make only 1 product. So I'll get 3 times less product than I do reactant. Does that make sense?
Yeah.
Okay, so how much product do we get? So it's 0.0057 times 1/3. How much is that? So 0.00057? Yeah. Moles times 1/3. What's that give me?
0.0019.
0.0019. Okay. Moles of Fe2CO3. Now, how am I going to convert that to grams? Because it says, my question is, what mass of precipitate? So I need to express it in grams.
You have to find the molar mass of the product and then.
Yep. So what is it? And you could look it up or you can calculate it. I like looking things up because I am lazy. Just remember, and this is key, remember to search for iron 3 carbonate. Because if you search for iron 2 carbonate, that's a different molecule. It's much smaller. Iron 3 carbonate is bigger. So make sure you get the right, make sure it's Fe2CO3 to 3. So what's the molar mass? It's going to be big, right?
291.7167 grams.
291 point, sorry, what was the rest of it?
291.7167 grams.
7167 grams per mole, right?
Yes.
Okay, so what do we do with that information to give us grams of Fe2CO3?
You multiply it by you multiply 0.0019.
Yeah, I just multiply these two together because this has moles as a numerator, this has moles as a denominator, and the unit we're left with is grams. So how many grams is that? Finally.
Five 5.5426.
5.5426 units, please.
Grams.
Grams, right.
2 CO.
So when you have your sodium carbonate solution, you're going to just basically just drop iron chloride in. Just keep dropping and dropping and dropping, just like in your experiment. And it's going to get cloudy and stuff's going to start to fall down. And you just keep adding it until no more stuff falls down. And then you get rid of the solution, probably wash it with some water, and then dry it. That's how you would actually do it in the lab. You would get rid of the water. You'd filter it. You'd filter it to get rid of the water. You'd wash it, the whatever your solid was, with water a couple times, because you know it ain't soluble in water. It gets rid of all the extra leftover iron, leftover chlorine, the leftover sodium. And then you would dry it, take your filter, you dry it in the oven. You get the mass of your filter. You'd weigh that before you dried it, or you would dry your filter until it achieves a constant mass, so you didn't have any water on it. Then you'd filter it, you'd dry it again, subtract the mass of your filter. You would get this mass. And how would you report it?
Would you take the significant digit too?
Mm-hmm.
It'd be 3 significant digits.
Yep, 3, exactly. So what's our final answer?
5.54.
Yep, exactly. Leave off the 2.6. So our final answer is 5.54 grams. Excellent. See, that only took us half an hour.
Professor, just I want to ask you, that number 291.716, this from Google, I have to say, like when I search, I have to find, I write in Google the mass of this compound or what?
Molar
Yeah,
mass.
you just write in Fe2 bracket CO3 bracket 3 molar mass,
Molar mass.
and it'll spit it out. Or you could put in iron 3 carbonate molar mass. Either one should get you the same thing. I like typing in the whole formula, because then I make sure I get it right. So I would just put Fe2 bracket CO3 bracket 3 mass, and
So
it'll give it to you.
So I have a question on a test. Basically, in situations like this, we have to provide all of this. We have to show our work in like a big sheet, because it's like you have to figure out first the equation and then.
Mm-hmm. Yeah, there's a lot of work. There's a lot of work for this sort of question. Yes, you have to show all the steps.
Okay.
Yeah.
So in general, just the highest concentration would be what creates the precipitation?
No, not the highest. The lowest concentration. Because we don't know how much iron 3 chloride was added. We just know it was excess. It was more than required. So actually, that leads to some of the other questions on the sheet. We know that the concentration of carbonate is limiting. So the amount of carbonate limits the amount of product we get. And we know that because the other one is in excess. And so when we wrote out the whole formula of the reaction, if one of the reactants is in excess, automatically the second one has to be limiting. Has to be. You can't have 2 things in excess. Eventually the reaction is going to stop because one of them runs out. And the one that runs out first, that's limiting. So in this reaction, if one of them is excess, by definition, the other one is limiting. So we use so notice we were given the concentration of the sodium carbonate. We're never given the concentration of the iron chloride because it's irrelevant. It doesn't matter because we just put more than enough of it. And we'll do some more of these to show, like, if you don't, some instances you don't know which one is in excess, and you have to figure out which one is in excess and which one's limiting. In fact, why don't we do one of those?
So I have a question.
Mm-hmm.
In order to find which one reacts with what you just find a strong ionic interaction.
Oh, when we figured out which one was the precipitate?
Yes.
Yeah, so that we pretty much figured that one out because it was the only one that made sense. Because at the end, so we had sodium plus carbonate together. We know that doesn't precipitate because they're in solution. That's one of the reactants. And we know that iron plus chloride doesn't precipitate because that's the other reactant. And we pretty much know that, so the only two other things that could precipitate is sodium plus chloride. And we know that that doesn't precipitate because that's just salt. That's just salt water. And there's a ton of salt water. So that's not going to precipitate. So the only possible thing left was iron 3 and carbonate. And then I mentioned that that is the most likely one because if you have a metal with a high charge density and you have a polyatomic ion with a high charge density and you bring those things together, that's a very strong interaction and they'll tend to crash out. So if you have trouble, let's say you have two other ions, they're not sodium and chloride, and so you don't know which one is going to precipitate. If you had to guess, pick the ones with the high charges. Those are more likely than others to precipitate.
And is it metal is always in the beginning of the equation?
Always, yeah. In an ionic compound, the metal always comes first, plus, then minus. Yeah.
Professor, when I calculated 0.0019 times 291.7167, I got 0.55426. Like the decimal
Okay.
place was moved back. Does that make a difference or?
Yeah, well, that's what we got here too, 5.4426.
I got 0.5.
Oh, we were off by a factor of 10?
Yeah, I believe so.
Oh, that's going to happen. Okay, so it's 0.55426, not
Yeah.
5. That did seem a little high, to be honest. Okay, yeah. So our final answer would be 0.554. Yeah. Again, if you gave the answer 5.54 grams, you would get like 90% of the points. Because you went through all of that and then you made like one dumb mistake on the calculator. And believe me, I do that all the time. So, but if you showed all the steps, and you know, obviously you did the calculations right because you had the numbers right. You just missed a factor of 10. And you know, believe me, biologists do that all the time. Chemists make fun of biologists all the time for doing that. So yeah, you'd get. But if you didn't show any work and gave the answer 5.54, you'd get nothing. Because you didn't show your work. I don't know where you got that number from. And it's wrong by a factor of 10.
We are done with this question?
I don't think we can milk any more out of this question. Yeah, let's do another one.
Yes.
Okay, so who wants to pick the next one?
Can we do number 5?
Okay, anyone else agree with that?
Or number 4? Number 4 maybe, I don't know. Whatever.
What would people like, 4 or 5? We'll probably do like half of these. We'll do like 4 of them, maybe 5 of them. Because you got to do some of them yourself. So what do you think, 4 or 5? Everyone's so quiet. Because there's some of these things you don't know about, right? Because one of them has titration involved.
We do.
So that's a titration question. That's a titration question too. So I'll do one of them. You can figure out the other one. How about that? So what would you like, 4 or 5? Those are acid-base questions that I did mention at the beginning. We haven't learned about acid and base, but it's fairly straightforward to do the reactions. So I'll show you how to do it. So it's basically the same question. So 4 or 5, what do you think?
The hardest.
Really, they're the same thing. Let's do 4. Okay, so we didn't get to the final 3 slides of chapter 2 were basically naming acids, and we didn't get to them before we ran out of time. So super briefly, an acid is, so instead of a typical ionic compound has a metal, right, and a non-metal, and when you put them in solution, they completely ionize, and so all the metal ion becomes positive, and all the non-metal ion becomes negative. Well, when you put hydrogen as your metal, it doesn't always completely dissociate and ionize. It does if they're what's called strong acids. And you're probably familiar with the term strong acid, right? So an acid is basically a hydrogen plus a non-metal ion. And it could be a single atom like chlorine or bromine, or it could be polyatomic like phosphate or sulfate, or something like that. And so here we have hydrobromic acid. What do you think hydrobromic acid is, if you had to guess?
Hydrogen and bromine combined.
Yeah, exactly. It's hydrogen and bromine. So it's just HBr. HBr is one of the strong acids. The basic strong acids are hydrochloric acid, which I'm sure everybody's heard of. You've got it in your stomach right now, dissolving your food. There's hydrobromic acid right there. There's hydroiodic acid, HI, so hydrogen with iodine. That's a strong acid. There's sulfuric acid, which is H2SO4, so that's hydrogen plus sulfate. There is, on the next question, is phosphoric acid, and that's 3 hydrogens with phosphate. That's a weak acid, which is good because phosphoric acid is in Coca-Cola. And it's bad enough that if you leave a tooth in some Coca-Cola, it will eventually dissolve completely. So it does. So you want to, rinse your mouth out after you drink some Coke, because it's fairly acidic. So this is strong. This is strong. This is strong. That's strong. So when you dissolve those in water, they release a lot of hydrogen ions. And anyone know how we measure how acidic something is? What measure do we use to measure the acidity of something?
pH level.
pH, exactly. pH. What do you think the H stands for in pH?
Hydrogen.
Yeah, exactly. So basically pH just tells you what the concentration of hydrogen ion is in a solution. So if it is pH 6, that means the concentration of hydrogen ion is 10 to the minus 6 molar. If something's pH 4, that means the concentration is 10 to the minus 4 molar. Because in this instance, minus 4 is bigger than minus 6, right? So the smaller the pH is, the smaller the number, the more acidic it is. So the pH in your gut, in your stomach, is around pH 2, maybe even a little bit less. And so neutral pH, pH 7, means the concentration of hydrogen ions is 10 to the minus 7. Which even when something is neutral pH, there's still hydrogen ion in there. There's constantly this reaction going on. H2O goes to H plus and OH minus. This is what we call a neutralization reaction. This is the acid, This is the base. And that's the reaction we're going to do in this question. So an H plus and OH minus, this is hydrogen. Anyone remember what that's called? What that ion is called? It was one of our oxygen-containing ions. We sort of went through quickly the other night. Hydroxide, that's right. That's the hydroxide. So magnesium hydroxide is a base. So hydrogen plus, also known as hydronium ion, and you'll see this sometimes because it generally associates with water. So this is called hydronium ion. It's the same thing as H plus. It's just H attaching itself to water being carried around. So H plus OH minus gives you water. And that we call it neutralization, because we've taken something acidic and something basic, brought them together, and now it's neither acidic nor basic. So with all that, we need to write out what our reaction is going to be. So we have figured out that we have HBr, that's our hydrobromic acid, plus magnesium hydroxide. So what's going to be the formula for magnesium hydroxide? First of all, what's the symbol for magnesium?
Mg.
Mg. And what's the charge on magnesium?
+2.
+2. It's always +2 because it's in group 2, right? So it's +2, and hydroxide
OH.
is what charge?
Negative.
It's negative. Negative how many?
1.
Right, it's -1. It's always -1. So what's going to be the formula for magnesium hydroxide?
I think it's gonna be same MgOH because 1 balance.
No, because magnesium is +2
Oh, okay.
and hydroxide is -1. So what's going to be the formula?
OH 2, like
So brackets 2,
Yeah.
right?
Yeah.
Right. So this is going to completely ionize, and this is going to completely ionize. So what does HBr going to give me in solution? So just think of it as an ionic compound. It's a strong acid, so I put it in, and what's it going to do? So if that was NaBr, that was sodium bromide, what ions would I get? So we just went over it the last question. What happens when you put an ionic compound in water? And it's a solution, so we know it's in water.
Is it H plus Br?
H plus and what?
Br? Bromine?
It's not bromine, nope. It's not going to be bromine when it's in solution. What's it going to be?
Bromide.
Bromide, there you go. Right, so we put that in water, we're going to get H plus, and we're going to get what?
Br?
Or 2.
Nope, nope. What's going to be the charge on bromide? Always, always, always.
-2.
Nope. It's in group 7, so it wants 1 electron to get to the happy place.
A 1 minus.
1 minus, right. So we're going to have H plus and Br minus. And we're going to have, when magnesium hydroxide dissolves in water, what are we going to get?
Mg plus 2
Yep. And what else?
plus OH minus 1.
How many?
Did you see how?
1.
Hmm? Nope.
Or is it
2.
0? Who said 0? We got to have some.
2.
2, right. 2. Because for every 1 mole of magnesium hydroxide we dissolve in water, we get 2 moles of hydroxide ion, because there's 2 moles of hydroxide ion associated with every 1 mole of magnesium. That's why we just sort of bang on moles all the time. It's all about moles. It's one molecule of magnesium has 2 molecules of OH minus on it. So for every 1 mole of magnesium hydroxide we dissolve, we get 1 mole of magnesium, but 2 moles of hydroxide ion. And remember, our product is going to be water. And the bromide and the magnesium are basically, remember what we call those ions that don't do anything? What do we call them? They're there at the beginning and they're there at the end, and they don't do a damn thing. They just stand around and watch. So we call them
Spectator ions.
spectator ions. So these are spectator ions. We don't really care about them because they don't do anything. So we could basically ignore them. So what we call our net ionic equation, what's actually happening is, and I'll sort of H plus 2 hydroxides give water. But that's not balanced, is it? We need to balance that equation. How are we going to do it?
So in the reactant, you'll put in the product, you'll put 2 H2O.
Mm-hmm. What else do I need to do?
You need to do on the reactant 2 hydrogen.
That's right. We need 2 moles of hydrogen ions for every mole of this magnesium hydroxide that's present, because the magnesium hydroxide releases 2 moles of OH minus. So basically we need twice the amount of acid. We need twice as much of this stuff, of the acid, this is the acid, then we do that, and that's the base. Because the base is throwing off 2 hydroxides, and the acid's only throwing off 1 H plus. So we need twice as much. So the question is, how much acid do you need in the presence of so much base? So we need to figure out how much base. It's all about that base. So how much base do we have? How much magnesium hydroxide do we have?
25 milliliters of
Mm-hmm.
0.222 m.
25 mils of 0.222, that's a kind of suspicious amount, molar magnesium hydroxide.
So you'd have to convert the milliliters to liters.
Yep. So what's that conversion?
So 25.0 milliliters times 1 liter over 1,000 milliliters.
Mm-hmm. Yep. 25 times 1 over 1,000. So that's 0.025 liters, right? Is that correct? 0.025 liters?
Yes.
Yes. And you ever want to check, just move it over the number. So if there's 1,000, we changed it by 1,000, you go 10, 100, 1,000. Yep, that's right. 0.025 is equal to 25 mils. So we have 0.25 liters, 25 liters times something gives us moles of magnesium hydroxide. So what do we multiply our 0.025 liters by to give us moles? Concentration, right? Volume times concentration gives you amount. We always do that. What's our concentration? What's the concentration of magnesium hydroxide?
0.222
Units, I need units.
molar or more mole per milliliter.
Nope. Moles per
Liter.
liter. There you go. Yes, so it's 0.025 liters times 0.222 moles per liter. So we get rid of liters and we're left with moles. So how many moles is that?
Zero point 00555.
555 moles of this. Now, still got some work to do. So now we know how much magnesium hydroxide is in the solution. Do we know what the concentration of hydroxide is in the solution? How much hydroxide is that?
1/2.
You've made the same mistake twice.
Or 2.
Yeah, twice as much, right? Because 0.00555 moles of MgOH2 times gives you moles of OH. So you have OH over MgOH. And for every 1 mole of MgOH2 you get 2 moles of OH, right? So we have twice as much. So how many moles of hydroxide do we wind up with? Is it 0.01111, something like that? 0.0111, I think. Is that correct?
0.0111.
0.0111 moles of hydroxide. Okay, almost done. So if that's the amount of hydroxide that's present, how many moles of H plus do we need to balance it out, to neutralize it? We can look at our net ionic equation. And our net ionic equation is here. Right? So here's my, there's my 2 moles of H plus 2 moles of OH minus give me 2 moles of water. So what's the ratio of OH minus to H plus?
Is it 1?
It's 1, right? It's 2 over 2, or 1. So for every mole of hydroxide, I need a mole of H plus. And it's only because this particular base dumped twice as much hydroxide, the concentration's twice as much, that I now need twice as much acid. But the ratio of my hydroxide to H plus is always 1:1 because they react in a 1:1 ratio to form 1 mole of water. So it's the same amount. So I'll need the same amount of H plus. So how am I going to figure out what volume of H plus I'm going to need? Because basically now I have an amount and I have a concentration. Here's my concentration. So I have an amount, a concentration, and I need a volume. So I take this, and I need to multiply that by something to get me to liters.
Point 125 moles over liters.
Yeah, 1.25 moles, H plus, because for every mole of hydrobromic acid, for every mole of HBr, I get 1 mole of H plus and 1 mole of Br minus, right? So the concentration's the same over 1 liter. So, oh, wait a minute. I need to flip it, don't I? I need to flip that. I almost made a mistake. That's why I always make sure I multiply. Oops, I did it myself. So 1 liter over 0.125 moles. There we go. H plus. So now my moles cancel and I'm left with liters. So how many liters is that?
Zero point 0.0888 liters of OH. Of
HBr. Yeah. So how many significant digits? Three, right, because there's 3 significant digits here, there's 3 significant digits there, and there's 3 significant digits there. They all have 3. So I would report my answer in 3. And so that could be the answer, 0.0833 liters, or if you wanted to give it in milliliters, what would be your answer in milliliters? Because you can see that they gave you the volume of the base in milliliters. So if you wanted to give the volume of the acid in milliliters, what would be the volume in milliliters?
Divide by 1,000.
So remember, milliliters are larger. The milliliters are smaller than liters. So the number of milliliters is larger.
Yeah, multiply with 1,000.
Well, don't just do that. If you multiply that by 1,000 milliliters is 1 liter. Yeah, so you would multiply by 1,000, but in order to make sure you do that, cross out liters and you leave milliliters. So what would my final answer be? In milliliters.
83.3 milliliters of
Yes. Yep.
hydrobromic.
Yep. There you go. Yeah. So again, a lot of work on these.
Wait, Professor, I got
Yeah.
0.0888 before like significant digits.
Oh, did we do that again? Did we screw up No, I think 83.3 is right. And I'll tell you why. Because you have 25 milliliters of base, and the concentration's 0.222. So we know that that's like twice as much. So the concentration of base of OH is going to be twice that, and our concentration of acid is less. So yeah, so it's got to be around 83 or so. So you got 8.3 as your final answer?
For before significant digits, I got 0.0888.
It's because you have to multiply the 0.00555 moles times 2 because of the ratio.
Oh, got it. Thank you.
Yeah. There's 2 moles of hydroxide for every 1 mole of magnesium hydroxide. Yeah. That's how we wound up with 0.0111 rather than 0.0555, because there's twice as much. Concentration's twice as high.
So I have a question.
Okay.
On the liter, 1 liter over what it's 0.125 moles of
H plus.
H plus.
Yeah.
How did you get from H plus to HBr?
Because for every mole of HBr, I get 1 mole of H plus. So the concentration is the same. The concentration of HBr is the same as the concentration of H plus. That's different than the magnesium hydroxide, where the concentration of hydroxide is twice as much as the concentration of magnesium hydroxide, because there's 2 molecules of hydroxide for every one of magnesium. But with hydrobromic acid, it's just H plus Br. There's just 1 H for every 1 Br.
One ratio.
So the concentration is the same.
Okay, I get it.
Yeah, so the concentration of the acid is going to be the same as the concentration of the H plus, where the concentration of the base is half as much as the concentration of hydroxide.
So the final answer is gonna be 83.3 milliliter.
Yep.
Okay.
Yep.
Next question.
All right, we got time to do one more.
Professor, just a quick question.
Yep.
Here, can you go back to the page and you delete?
We'll try. Yep, there we go. I love
Okay.
that undo button. It's awesome.
Okay, just in the beginning, when the answer was 0.08333, the first and the second zero, they are not significant, correct?
That's right.
Okay.
That's right. So these 2 zeros are not significant because they only tell us how big the 833 is. That's it. They just tell us, they just move the factor of 10 around. So it's either 0.833 or it's 8.33 or it's 800ths or it's 8,000ths. Yeah, it doesn't, those zeros just tell us what factor of 10. If you ever wonder, this is I find the best way to figure out whether they're significant or not, is put it in scientific notation. So if you were to put this number in scientific notation, those zeros would be gone, right? Because the number would be 8.33 times 10 to the minus 2. Those zeros would not show up, so they're not significant.
Can we do question 7?
Professor, how did it
Okay.
become 0.0833? I'm kind of confused.
Oh, man, there's a lot going on here. So we had, let me see if I can erase some of this stuff.
Because when I multiplied 0.0555 times 2, I get 0.0111. And then when I multiply that to 0.125, I got 0.08888.
Oh, we may have made a mistake with that's possible. Yeah, because basically 0.125 is just multiplying that number by 8. So I think you're right. Yeah, I think that number, so this multiplied by this, I think you're right. I think that's 0.0888.
Yeah, correct. Yeah.
That is right. Yeah. Good spot. Good call.
Thank you.
Yeah, because 0.125 is basically 1 over 8. So oops. But like I said, if you showed all that work and had like the wrong answer, you'd still get 95% of the points because, man, you spent half an hour working on it. You made one mistake with the calculator. No biggie.
And
Yeah, so our correct answer would be 88.8 mils. Yeah.
oh, so you just have to convert it to milli.
You don't have to. You don't have to because the question just says what volume. Doesn't tell you what units to use. I was just saying because the units of base were in mils, we might as well put the unit of acid in mils. But it doesn't say, unless it strictly says like what volume in milliliters. If it doesn't say that, let's leave it in liters. That's fine. Or convert it to quarts. I mean, it doesn't say, so you can put whatever units you want.
Okay,
You could convert it to gills if you really want to.
Can we do either 7 or 8?
Oh dear, someone sounded bad about that. I'm going to let someone else choose.
Okay.
Can we do one of the equations from the table? I couldn't understand that really well.
The table, okay. They can briefly show that one clear. That's number 6, right?
Yes.
Okay. Yeah, so this is a reaction. It's actually balanced. That's good. You don't have to do that. So it's just nitrogen gas plus chlorine gas gives you nitrogen trichloride. And so at the beginning of that reaction, you've got 100 grams of nitrogen. You've got 125 grams of chlorine. I think what happened is like before, like I think on your worksheet, the nitrogen is over this one, the chlorine is over this one, and the nitrogen trichloride's over that one. So at the beginning of the reaction, you have 100 grams of nitrogen, you have 125 grams of chlorine gas, and at the beginning, you don't have any product because the reaction isn't started yet, right? So then you just calculate how many moles, let me write it down, moles of N2, moles of Cl2, and 0. So you need to figure out if all of the nitrogen was converted to product, how much would you get? If all of the chlorine was converted to product, how much would you get? And then from that, you figure out which one of these is limiting. It's either this or this. So the answer to moles reacting or forming is going, for one of these two is going to be 0, is going to be all of it. And one of them will have nothing left at the end, and the other one will have something left at the end. So you need to figure out which one is the limiting reagent. Is it nitrogen or is it chlorine? And how you figure that out is you calculate, you take your moles of take your moles of nitrogen, right? So here you've calculated moles of nitrogen. Using the balanced equation, man, I'm having trouble with my screen. So using the balanced equation, convert all of it to product. And then chlorine, same thing. Using the moles of chlorine, convert all of it to product. One of those numbers will be smaller. Whatever number is smaller, that's your limiting reactant. So if I get less product when I convert all my nitrogen to product, that's my limiting reaction, my limiting reactant. If I convert all my chlorine to product, and it's less than if I convert all the nitrogen to product, then the chlorine is the limiting reactant. You see what I mean? One of them is going to give you less product than the other. You need to figure out which one. And then from that, one of these two, either the nitrogen or the chlorine, or let's say that's like 3 moles of chlorine. If that's the limiting reaction, you're going to use all of it. All 3 moles are going to be used, and then there'll be none left at the end. But for the nitrogen, you're not going to use up all of it. It's going to be excess. So you have to figure out how many moles of nitrogen. Let's say there was 3 moles of nitrogen at the beginning, but you're only going to use 2 because it's an excess. So I would only use 2, and there'd be 1 left over. So at the mass at the end, this would be none because you don't have any chlorine left, and you would just convert your 1 mole of nitrogen to grams. And here, the same thing. You'd figure out what the limiting amount of product would be, and then convert that to grams at the end, okay? So yeah, so there's a lot of calculations here. You need to figure out which one's limiting, who's limiting, and how much is left of the excess reagent. If you have any questions about that, we can go over it after you've had some time to work on it. So that's how you would do that one. So we've got like 20 minutes left. We have time to do one more. So Someone suggested either 7 or 8. Is there one in particular?
The one has new idea, like he knew something to practice.
Let's see, which one? Which one would that be?
You have the equation for the percent yield?
Oh, yield. Oh yeah, so one's what? Yeah, one is yield. So yield's pretty straightforward. Yield is just so this question. What's the formula for disulfur dichloride? You should know what that is.
S2Cl2.
Yep, that's right. S2Cl2 is your product. And you make it by reacting chlorine gas. So remember, chlorine gas is not chlorine. It's Cl2. And it sort of tells you right there. And molten sulfur. And if you remember, the most stable form of sulfur isn't just sulfur by itself or even sulfur 2. It's S8, which is kind of weird. So basically, you have to balance this equation. First thing you do with any chemistry question involving reactants and products is balance it, okay? So how would we balance that reaction?
4Cl2 for the reactant, and then
Okay,
and then it's 8, and then it'll be 4 for the product S2Cl2.
all right, so that gives us 4 chlorines, 8 sulfurs. Yeah, nice. All right, so if you have 10 grams of this and 6 grams of that, you have to figure out how much of this you get, okay? Now, what yield means, if you figure out how much of this is made, that's with the assumption that this reaction goes to completion, goes all the way to the end, and one of these two gets consumed completely, and you get 100% of the product back. Basically, it means that at the end of the reaction, I get to isolate all of the product. And in real chemistry, that doesn't happen. That never happens. You never get to isolate all of the product. You're always going to lose some. Generally, you lose some in trying to purify it. Because at the end of this reaction, it's going to be messy, right? You got molten sulfur. So that's going to smell awful, and it's molten, it's hot, and you've got chlorine gas all over the place. And so it's going to be nasty. And so you're going to be left with this sort of nasty product, and you have to separate it from all this other stuff. And so it's usually in the separation that you lose some of your product. Some of it's going to like stick to the sides of whatever vessel you get in. You're not going to be able to scrape it off. All sorts of reasons. So if you get 100%, if you were actually able to capture 100% of the theoretical product, and remember, this is theoretical. We don't actually know. Theoretically, if we had 6 grams of chlorine gas and 10 grams of molten sulfur, theoretically, if everything went perfectly, this is how much product you would get. And that's from your calculations. You don't get that. So 85% yield would mean we only get 85 out of 100 of that. So what you would do is just figure out what the theoretical yield is, where you get 100% of the product. All of it goes to completion, and just multiply it by 85%. That's it. That's all yield means. It's super simple.
The theoretical, is that the total of the two numbers?
Oh, reaction. Oh, the yield just means product. Yield doesn't refer to the reactants, only product. Because when you do a reaction, basically you're only interested in making product. You don't care about you don't want the reactants. You want them to all go away.
Would it be the sum of the reactants, which would be the product? Would it be the sum of the reactants?
No. What do you mean?
In order to get the theoretical yield.
No, because you don't know. One of these might be limiting. Yeah, if this was a perfectly balanced reaction and you had perfectly balanced amounts of both reactants, then yes, theoretically, you should get 6 plus 10 equals 16. But you don't know whether or not you have exactly the right amount of chlorine and exactly the right amount of sulfur. You need to calculate that. But you're right. I mean, if you did everything right, and you had exactly the right ratios of reactants, yeah, they'd go away completely, and all of it would be converted to product, and all would be happy and joyful. That's not the life of a chemist, I'm afraid, because you're not going to get a perfect yield. You're always going to have, pretty much, you're always going to have one reactant in excess. And the reason you always have one product in excess is to guarantee that the reaction goes to completion. Generally, whatever reactant is less expensive, you know, if there was a sale on chlorine gas that week, you just use all the chlorine gas you could, and just to make sure that all that sulfur got converted.
So
That's usually how we do it.
what would you multiply the 80% yield to?
You would figure out what's my theoretical yield? Which one of these two, the 6 grams or the 10 grams, one of those is limiting. Figure out which one it is. And then based on that, convert all of that limiting reactant to product. So that is the maximum amount of product you could possibly make given those two amounts of reactant. That's the most, just like the last question I showed you with the nitrogen, the chlorine making a nitrogen trichloride in the table. One of those things is going to be used up completely. That's the limiting reagent. And that determines how much product gets made. Same thing here. Either the chlorine or the sulfur is limiting. So because that's limiting, we use up all of it, and however many moles that is, that will determine the number of moles of our product. Okay? So that number is 100% yield. So theoretically, all of the product that would be made, we'd be able to get back. That never happens. And so we take that theoretical 100% yield and multiply it by 85%. That would be our actual yield. But for most reactions, if you get over 50, 60%, you're super, super happy.
Okay.
And I just got my lab kit today, so we're going to go through it. There's probably a experiment in there for you to determine percent yield. I know there was in our regular lab. The regular lab you would have attended. There's a couple of different experiments where you determine what your percent yield is, and it's never 100%. It's never even close.
Professor, can we answer this question, like to complete?
No, you do that.
Okay. And, when we gonna use the kit for the lab?
Well, we don't know when yours have arrived. We think ours arrived first, and there may be like another week or two before everyone else's get here. I'll let you know. Oh, so I just want to show you the last one too, because there's something new in there. Basically, it's not that new. It's just balancing equations. So it's a combustion reaction. We should know by now, a combustion reaction is just something that burns. Here's something that burns in the presence of oxygen, and we get CO2 and water. Now, that very clearly isn't balanced, right? So let's balance it. I'll show you how an easy way to balance these sorts of reactions, and then explain what STP is. Okay. So this is propene gas, not propane. Propane would be 1, 2, 3 with 1, 2, 3, 4, 5, 6, 7, 8. would have 8 hydrogens on it. Propene has a double bond in it. So it looks like this. So 1, 2, 3, 4, 5, 6. So C3H6. And we're going to burn it in the presence of oxygen. So oxygen is going to be in excess. In any combustion reaction, oxygen is generally going to be in excess unless you're doing it in a closed container or something. So who wants to, how do we balance these sort of things? Anyone remember what we start with? Which atom do we generally balance first? We have carbon, we have hydrogen, and we have oxygen. Where do we normally start?
Carbon.
Yeah, you can start with hydrogen. You can start with either hydrogen or carbon. Leave oxygen for last. So let's start with carbon. So I got 3 over here. I got 3 of them here. So how many, how am I going to balance that?
Three. So we're gonna put the 3 front as CO2.
Yes, so we put this, yeah, we put the 3 here. So that balances the number of carbon atoms. So then we do hydrogen next. So how are we going to balance the hydrogen? So I got 6
3
here.
from the water.
Yep, 3 from front of the water. Now I got to leave oxygen for last. So how many oxygens do I have on the as products? I've got how many total oxygen atoms?
9.
9.
9. So how am I going to balance my oxygen atoms on the left side? There's a trick. Does everybody want to know the trick? Nobody wants to know the trick. It's a good trick. I'll show you what it is. So we need 9 oxygen atoms on the as reactants, right? To match my 9 on the right. So I'm just going to cheat. I'm going to say, all right, I'm going to have 9 over 2. How about that? Now it's balanced, right? Problem is I can't have 9.5 molecules of something. There's no such thing as a half a molecule or something. So what am I going to do here?
Multiply with 2.
Multiply everything by 2. It's a whole damn thing. Just take the whole thing and multiply it by 2. So instead of 1, I'm going to put a 2 here. So instead of 9 over 2, I'm going to have 9. Instead of 3, I'm going to have 6. And instead of this 3, I'm going to have 6. Then check and see if it's balanced. So I've got how many carbons on the left? How many carbons as reactants do we have? On the left side is reactants. How many carbon atoms do I have?
6.
6. And how many do I have on the right?
6.
6. That's good. What about hydrogens? How many hydrogens as reactants?
12.
12. What about as products?
12.
Actually, it might make this easier if I just... Right, so 6 and 6. Yeah, also 12. I've got 12 hydrogens here too. And then finally, oxygens. How many do I have as reactants?
18.
18. And what about as products? I have 6 times 2. I got 12 here. I got 6 times 1. I got 8 here for total. Oh, no, 6. Duh. Sorry. So 12 plus 6, I got 18 oxygens. So it balances. And that's a classic way of balancing these combustion reactions. And you're going to have to do it a lot because there's an even number of oxygens in CO2, but there's an odd number of oxygens in H2O. And so there's always going to be an odd number of oxygens in your products. And since it's O2, you're always going to have an even number of oxygens as reactants. So the way to get around it is to just multiply by 9/2 or 11/2 or 15/2, whatever it takes to balance it, and then multiply the whole thing by 2. And so our final is 2 propenes plus 9 oxygens gives 6 carbon dioxides and 6 waters. That's our balanced reaction. So to finish the problem, so O2 is in, we have excess O2. So we don't have to worry about O2, okay? Let me put my numbers in here. All right, where are my numbers at? So 9, 6, 6. So I have 8.50 grams of this, okay? Now I'm going to convert that to moles because that's what we have to do. Convert that to moles and figure out how much CO2, how many moles of CO2 are formed. Okay? How many moles of CO2 are formed? That's really all you have to do. So what's the molar mass of C3H8? Figure that out. What it's 3 times 12, that's 20, 36 and 6. So it's going to be around 42 moles, right? 12 times 3, yeah. So it's going to be around 42 grams per mole. So figure out how many moles that is. Use the balanced equation to figure out how many moles of CO2 you would have. And then just use this conversion of 1 mole is equivalent to 22.4 liters. And we'll learn about that later when we learn about the gas laws. That at 0 degrees C, or 273 Kelvin, and 1 atmosphere of pressure, gases take up, 1 mole of gases takes up a unit of volume of 22.4. They all do. It doesn't matter what gas it is, because there's so much space between gas molecules that they all pretty much take up the same space. So you just use your balanced equation, grams to moles, mole to mole conversion of reactant to product. That gives you moles of product, and then just convert that to volume.
Just I want to know, 850, this is from Google, like I have to write molar mass?
850, sorry? Where does that come from?
This gram, the one you write it down.
No, it's right here. 8.5 grams of protein.
Oh, okay.
Yeah.
Oh, where did you get 42 grams per mole?
Oh, that's going to be approximate. You look up the exact amount, because it's 3 carbons, and the carbon is 12, that's 36. Hydrogens are 1 gram per mole, and they got 6 of them, so that's 36 plus 6. So it's going to be around 42, something like that. Probably a little more. Just look it up. Probably like 42.1 or 42.2 or something like that. Probably around 42.1. Just remember you put propene in and not propane, because those are different molecules. All right, man, went a little long today, but that's good. That's fine. So any other questions? I can maybe get you started on some of the other ones, but we're not really going to go through them all the way. But if you're confused, just by I know you haven't had a whole lot of time to look at these, but if there's something in them that you just don't understand, I may be able to sort of point you in the right direction.
Can we just give a head about number 3?
Number 3. Three. Okay. Yeah. So again, we have magnesium hydroxide, a certain amount. We have 45 grams of hydrochloric acid. HCl is hydrochloric acid. And it just basically gives you the reaction. So that would be Mg plus 2OH minus plus 2H plus Cl minus gives you Mg plus 2Cl. It's basically, this is the same, it's a neutralization reaction again, where the magnesium is spectator ion, the chloride is a spectator ion. So the overall reaction is 2OH minus plus 2H plus gives you 2 waters. So what you want to do is figure out what's the molar mass of magnesium hydroxide, what's the molar mass of HCl. Make sure this is a balanced reaction. Should be. And then all you need to do is figure out how much of MgCl2 you'll get. This was probably like the most straightforward there is. Just figure out how many moles. So for every 1 mole of Mg, OH2, you get 1 mole of magnesium chloride. For every 2 moles of HCl, you get 1 mole of magnesium chloride. So figure out how many moles are in 50.6 grams, and for this one, how many moles are in 45.0 grams. One of them is limiting. You need to figure out which one it is. So whichever one is limiting, assume all of it gets converted to product and use the ratios in the reaction, 1 to 1 or 2 to 1. Figure out how much gets converted to product. Because this is your product. You want to see how much of that you would get. Okay, so just convert to moles and then figure out what's the maximum amount of product I would get if all of this was converted to MgCl2. What's the mass product I would get if all of that was converted to MgCl2? Which one is less? And that's your theoretical yield. The one that gives you less. Okay?
So the answer is gonna be either MgOH or HCl.
No, the answer is going to be grams of MgCl2, because either all of this is going to be consumed or all of this is going to be consumed. Either all the MgOH2 is going to be consumed or all of the HCl is going to be consumed. You don't know which one.
Mm-hmm.
You need to convert both to moles and then use the balanced equation to figure out if I converted all of my magnesium hydroxide to product, how much product would I get? If I converted all my HCl to product, how much product I would get? One of them is going to be less. And that's going to be your theoretical yield. And the one that's less, that is your limiting reactant.
Can you repeat what's the meaning of limiting reaction?
So if I convert all of the HCl to product and I get 2 moles of MgCl2, and I convert all of my magnesium hydroxide to product, and I got 1.6 moles of MgCl2. This is limiting because I can't make any more product once this is consumed. Once I've used all that up, I can't make any more product. I'm going to have some of this left over. Some of this is going to be left over because when I consume, what this number means is if I consume all of this, that's how much product I make. It means I've got some HCl left over that doesn't, and if I want to figure it out, how much HCl is left over, I figure out how much HCl it takes to make 1.6 moles of product, and then how much is left over. All right, got about another 5 minutes or so. I got to take these doggies for a squeeze. Anything else? Everybody's good? It's a lot of work for you on the weekend. Sorry about that. A lot of calculations. Like I said, you don't have to do it on the paper. If you think you're going to use a lot more, then yeah, just write it out on whatever paper you got.
We can email you if we have any questions, right?
Of course. Yeah, of course. Yeah.
For recitation number 3, is there any way, like, if I start in one question, you can record the steps how you answer it?
I'm sorry, I didn't quite get that.
No, I said for recitation number 3 because I
Mhm.
remember there are some question a little bit hard and I couldn't ask you today in office hour. So if there is any way like you record yourself since we do not have time.
Oh yeah, if you're a week late with a recitation, that's no biggie. That's fine. I'm not going to get upset about that. It's
Will we
just
get
if you,
points taken off?
hmm?
Will we
No,
get points taken off? Okay.
no, if you're trying to pass them in at the end of the term, then yes. Because some people have done that in the past and ugh, it's craziness. But yeah, if it's like 1 week late, I don't even think about it.
No, I mean if I couldn't figure out the answer and I need you to explain how you do.
Okay. Yeah,
So
then
is
just,
there any way you record yourself like you make video and post it and can
oh, I see what you mean.
just in case.
Well, yeah, I mean, eventually you'll just get all the answers to these and how they're worked out. So you won't have a video, but you will have each step given in the answers. Rather than, I'm not like for instance, for this one, I'm just not going to give, the theoretical yield is like, 56 grams the end. I mean, I'm not going to, I'll show you all the steps required to get to it. Yeah.
I have a question. If we pass the lab report late, will you deduct points? Or
Depends how late. If it's like more than 2 weeks late, I might, but if it's less than 2 weeks late, I'm not going to.
okay.
Yeah. Mm-hmm. Again, that's just to try and keep people from, doing nothing whole term, and then like after, like I've had at least a couple students do nothing the entire term, and then take the final, and then try to submit like all this stuff like after the final. It's a nightmare. So yeah, basically anything submitted after the final, not really worth your while. You might get 40%. Okay. All right, everybody. Man, I am hungry. I will see you, 2 hours. Hardly time for a nap. All right, I'll see you in a little while.
Thank you.
All right. See you in a little while. Bye-bye.